Here we have the introduction to the Huntington-Hill method, also called the method of equal proportions. This method is mainly used to divide or apportion seats in the U.S. House of Representatives fairly among the states. What makes it unique is that it applies the geometric mean, which helps balance out the differences in representation between large and small states, making the process more equal and fair. Joseph Adna Hill was a chief statistician at the U.S. Census Bureau in the early 1900s. He wanted a fairer way to divide seats in Congress so that large and small states would be more equally represented. In 1911, he first proposed the equal proportions method. Edward Vermeil Huntington, a Harvard mathematician, later refined Hill's idea by introducing the use of the geometric mean. This made the method more precise and mathematically fair. Because of their combined efforts, the method was officially adopted in 1941 and has been the standard ever since.
The Huntington-Hill method, also known as the method of equal proportion, is the mathematical formula used to fairly distribute seats in representative bodies such as legislature among different groups, regions, or states based on their population. It works by assigning seat one at a time to group with the highest priority value, which is calculated using the population of each group and geometric mean formula. This method aims to achieve the balance so that representation is equal and fair possible, minimizing inequality between larger and smaller populations. So, in short, each group, state, or district, the first guaranteed one seat. The remaining seats are distributed one at a time using a priority value, also called priority number, and it distributes seats among groups based on population. It balances representation between big and small groups.
Definition of terms. The Huntington-Hill method used for apportioning seats in a legislature utilizes terms like standard divisor, quota, and geometric mean. For standard divisor, the total population is divided by the number of seats to be allocated, essentially representing the number of people per seat, used as the initial basis for calculating each state's proportional share of seats. Next is quota. The number of seats a state is initially assigned based on its population divided by the standard divisor. This can be a decimal value. Next is geometric mean. A crucial element in the Huntington-Hill method, calculated as the square root of the product of two consecutive integers. Example, the square root of 5 multiplied by 6. Next is rounding rule. In the Huntington-Hill method, a state's quota is rounded up to the next whole number if it is greater than the geometric mean, and rounded down if it is less than the geometric mean.
Alright, so here are the steps and procedures. Step 1. Find the standard divisor. The standard divisor is found by dividing the total population by the number of sets to be apportioned. Basically, you're figuring out the average population size that each set in a representative body should be represented. So you do this by dividing the total population by the number of sets available. Step 2. Find a quota. Each state's quota is determined by dividing its population by the standard divisor. Note that the quota may be a decimal number. Okay, so now for each set or group, you're figuring out how many sets they should get based on their population. Okay, so divide each state's population by the standard divisor you found in step 1. This gives you the quota, which might be a decimal number. Step 3. Find the upper, lower quotas and the geometric mean. So, find the next higher and lower whole numbers from the standard quota. The geometric mean is used as a threshold for deciding when to assign an additional set. So, upper and lower quotas. These are the whole numbers immediately above and below the quota you calculated in step 2. For example, if a state's quota is 4.3, the lower quota is 4 and the upper quota is 5. So for the geometric mean, this is a threshold to help decide whether to round a quota up or down. It's calculated as the square root of n times n plus 1, where n is the current number of sets assigned. Step 4. Round the quota. If the quota is greater than the geometric mean, round up. If the quota is less than the geometric mean, round down. When you add up the resulting whole numbers, you get the initial allocation. Here's where you decide how many sets each state initially gets. If a state's quota is greater than the geometric mean, round it up to the next whole number. If it's less than the geometric mean, round it down. And add up all the rounded whole numbers to get the initial allocation. Step 5. Final double check to finish. If the total from step 4 is less than the total numbers of representatives, reduce the divisor and recalculate the quota and allocation. If the total from step 4 is larger than the total number of representatives, increase the divisor and recalculate the quota and allocation. Continue doing this until the total in step 4 is equal to the number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. Alright, so this is the fine-tuning step. If the total number of sets you allocated in step 4 doesn't match the total number of representatives, you need to adjust the standard divisor. If you allocated too few sets, reduce the divisor. If you allocated too many sets, increase the divisor. Recalculate the quota and allocation with the new divisor and keep doing this until the total number of sets matches the number of representatives. The divisor you end up using is called the modified divisor or adjusted divisor. So that's all from steps and procedures. Thank you.
Problem, sample 1. So, suppose there is a legislature with 12 seats to be allocated among 3 provinces based on their populations. The populations of the provinces are Province X is 40,000, Province Y is 70,000, Province Z is 90,000. We need to allocate the 12 seats among these 3 provinces using the Huntington-Hill method. Sample 2. Suppose a council has 15 seats to be distributed among 5 regions according to their populations. The populations of the regions are: Region A is 35,000, Region B is 35,000, Region C is 50,000, Region D is 60,000, and Region E is 80,000. We need to allocate the 15 sets among these 5 regions using Huntington-Hill's method. Solution, sample 1. Apportioning 12 sets among 3 provinces. Populations of the provinces are: Province X, 30,000, Province Y, 70,000, Province Z is 90,000. And here's the formula. Priority value equals P divided by the square root of S times the quantity S plus 1, where P is population and S is current seats. And here's the step-by-step process. Give each province 1 seat first. 2 is calculate the priority values using the formula. 3 is assign the next seat to the province with the highest priority value. 4. Update the set count and recompute priorities. 5. Repeat the process until all 12 sets are allocated. Sample 2. Apportioning 15 sets among 5 regions is 5 regions of the regions are Region A, 25,000, Region B, 35,000, Region C, 50,000, Region D, 60,000, and Region E is 80,000. And here's the formula, priority value equals P divided by the square root of S times the quantity times the quantity S plus 1. Here's the step-by-step process. 1. Give each region 1 seat first. 2 is calculate the priority values using the formula. 3. Assign the next set to the region with the highest priority value. 4. Update the set count and recompute the priorities. 5th is repeat the process until all 15 sets are allocated.
For sample 1, apportioning 20 representative among 3 provinces. Now there are 3 provinces and each province has its own populations. Province X 40,000, Province Y 70,000, Province Z 200,000. Now their quota in each is for Province X is 2, Province Y 3.50, Province Z 4.50. Now their lower quota is just simply by cancelling the decimal digits. So 2, 3, 4, 9. Now the geometric mean, it has a formula that we follow. So the geometric mean for Province X 2.449, Province Y 3.464, Province Z 4.472. So now the initial allocation is 2, 4, 4, 10. Now it equals to 20. For sample number 2, apportioning 15 sets among 5 regions and each region has its own affiliation. For Region A, 25,000, Region B, 35,000, Region C, 50,000, Region D, 60,000, Region E, 80,000. Now, their quota in each region is for Region A is 1.50, Region B, 2.10, Region C, 3, Region D, 3.60, Region E, 4.80. Now, their lower quota is just removing the decimal places. So, 1, 2, 3, 3, 4. And geometric mean there is formula that we follow. For Region A, 1.414, Region B, 2.449, Region C, 3.464, Region D, 3.464, Region E, 4.472. Now, same goes with the initial allocation of quota bigger than geometric. Then we add up, and if its quota is smaller than geometric mean, and then we stay for the number. So for Region A, 2, Region B, 2, Region C, 3, Region D, 3, Region E, 5. So total of 15.
In conclusion, the Huntington-Hill method plays a vital role in ensuring fair and proportional representation, particularly in the distribution of seats among states or groups based on population. By using the geometric mean as its divisor, this method provides a balanced and more equitable allocation. Compared to other apportionment methods, minimizing both overrepresentation and underrepresentation, it highlights the importance of mathematics not just in numbers but in shaping governance, decision-making, and democracy itself. The method teaches us that representation should not be left to chance or a preference, but must be rooted in objective calculations that give each individual and each group their fair voice. Ultimately, the Huntington-Hill method serves as a reminder that mathematics is not only a tool for solving problems in classrooms, but also a guiding principle for fairness, justice, and equality in real-world systems of government and society.